Hi, I'm Deborah Ferguson, a postdoc at the University of Texas at Austin. And today I'm excited to tell you guys a little bit about some of the work that I have been doing on optimizing numerical relativity placement using neural networks. So as we think about the next generation of gravitational wave detectors, including LISA, Einstein telescope, Cosmic Explorer, we need to think about what is going to be necessary in order for numerical relativity to be prepared to analyze the data that they're going to present us with. And as you can see on this figure on the right, we have plots for LISA and Einstein telescope showing the color contours are the signal to noise ratios of events of given total mass detected at a given distance on the right or redshift on the left. And what you can see is that we expect many signals to fall in the hundreds SNR, and we expect some even to be seen up to 3,000 or higher. So this means that we are going to require extremely accurate waveforms in order to process these in such a way that we don't contaminate other signals or get false positive for testing beyond theories of GR. And it also means that we will require very dense template banks of numerical relativity waveforms that are also highly accurate. And the challenge here is that numerical relativity simulations are very expensive and time consuming. So we need to make sure that we are very intentional in how we approach filling out this parameter space. So what's the state of the parameter space currently? Well, here we show the NR groups of SXS, RIT, and Maya. They're public catalogs, and a couple caveats to this plot. One is that this does not include mass ratios higher than 15, and RIT does have some waveforms at higher than 15 mass ratio, but it skewed the plot, and I felt like this was more informative, but I do think it's important to note that RIT does have some higher mass ratios. Also, these are only non-eccentric events or non-eccentric simulations. So what you'll notice in this plot is that for lower mass ratios, we tend to have simulations that span the spin range for each of the components for each of the black holes. So here we've got the primary black hole, and here A2, we have the secondary black hole, each of the spin components. And you can see for mass ratios up to 5, or 4 rather, we have decent coverage in all of that parameter space. Then you'll notice that we have some, but very few aligned spin simulations beyond that, but essentially no processing simulations beyond mass ratio 5. So we definitely know that there's a gap here that needs to be filled in, but you can also see that there are some gaps even within the existing parameter space that is densely filled that we would also like to explore. So what is the goal of this project? Well, we want to optimize how we fill in this parameter space. We want to select the next NR simulation to run within given bounds in order to optimize the benefit of that simulation. So how are we doing this? Well, we train a neural network to predict the similarity between two waveforms based on the initial binary parameters. And to quantify that similarity, we use the match. And then the next step is to use that neural network to identify gaps in the parameter space and select the next most optimal simulation. So here is a diagram outlining this. We can see that we put in the symmetric mass ratio and each of the spin components for the first simulation, and the symmetric mass ratio in each of the spin components for the second simulation. And then we predict the match that would be between those waveforms. So our training set consists of the total data set consists of 1,885 simulations from the SXS public catalog. This is broken into 1508 training, 188 development, and 189 test simulations. The actual data points that go into the network are all possible pairs of each of the simulations within a data set. and their resulting match. The matches are computed with a minimum frequency of F lower at 1M sun equals 1840 Hertz. And right now they are computed on just a flat noise curve, so independent of mass, etc. The network architecture consists of 15 layers, each with 56 nodes. The hidden layers use the ReLU activation function, and the output layer uses a sigmoid activation function. We use an atom optimizer using the mean absolute error as the loss and a learning rate of 0.001. And now for the results. So you can see that the test error, the final result, is that we are able to predict the match to within 0.018. And you can see the spread over here on the right of the true values and the predictions. So we are able to predict the match that would result from two input simulations without actually performing those simulations. So this accuracy does vary across the parameter space, which makes sense because we have training points more densely in certain areas. So what this plot shows is these plots show the mean absolute error as a function of different aspects of the parameter space. So because we input two simulations, we plot here the light blue referring to the first simulation and the orange referring to the second simulation. And so here you can see that around mass ratio 4, 3 and 4 is actually where you seem to have the highest error. And then you can see over here the difference in mass ratio. So how different is the mass ratio between the two simulations that you're comparing? And you can see there's a bit of a spike around 6 and a bit of a spike around 2.5. This shows the mean absolute error binned by the primary and secondary spin magnitudes. And you can see in general that as you increase the spin magnitude, the errors go up. This shows the errors for chi-effective and chi-processing. And you can see that for positive chi-effective, the errors are actually pretty decent. But for negative chi-effective, we see this spike around negative 0.5. And then in the second plot, we see chi-processing, and we see that as you increase the precession, you increase the error, which is consistent with the fact that we have fewer processing training simulations. So it makes sense that the error grows. Here we have a plot showing each of the individual spin components, primary on top, secondary on the bottom. And you can see that for spin 1x and spin 1y, as you move away from 0, the error increases. And for spin z, you see this spike again at negative 0.5, consistent with what we saw in the chi-effective and chi-processing plots. The secondary spin seems to impact the error less, which is consistent with the fact that secondary spin tends to impact simulations, tends to impact the waveform less, though there is this spike for A2Y at negative 0.75 or so. So then the next step, now that we have this model, it works decently well and we can utilize it. So for utilizing the model, what we show here is suggested simulations selected so as to minimize their match with the existing Maya catalog. So in blue here, we see the parameter space coverage of the existing Maya simulations. And then in red is the suggested new simulations, where the shade denotes the order in which they were suggested, with darker meaning earlier. And you can see how it starts to fill in the space. Naturally, it's pushing to the borders, but as you continue to get more simulations, if you keep the bounds the same, it'll start filling in these gaps as well. So in conclusion, we are able to predict the match between two waveforms based on the initial parameters of the simulation quickly and effectively. And we can use this to carefully place future simulations. And this will allow us to use our resources more efficiently and prepare the dense bank of numerical relativity simulations that we would like for future detectors. Remaining work, we would like to train this on other noise curves in order to have detector-specific suggestions for what simulations you should run next. Also, we will continue to iteratively improve this model by running simulations at the suggested locations, running targeted simulations at the boundaries of parameter space that we would like to push, and then retrain on those simulations in order to create a more accurate network. Thank you for your time.